Okay, we are ready to look at some problems and examples related to the Cascode amplifier. Okay, that's the purpose of this recording. So let me move ahead to where the first numerical example is, and that is on page or slide 25. So this is an example worked out in the textbook. It's on page 512, and in fact it's the only one in this whole section, only example that is given in the textbook for this whole section on cascoding. But I've looked at it. It's a pretty nice example. It covers a lot of material, so you should definitely become completely familiar with all the steps in this example. So a cascaded current source, right? So this Q4 is the current source. It's connected to the VDD, the battery, and it has a friend, which is the cascode transistor Q3, and both of these are PMOS devices. So current of 100 microamps has to flow like this along the drain and sources, and there is an output resistance of 500K. RO is 500K. Also, other items given, other pieces of data, VDD is given 1.8, VT for the PMOS is given, Kn, this factor is given 90 microamps per volt square, and the early voltage parameter VA prime is given. It's a negative value for PMOS. Lastly, using overdrive voltage of 0.3, determine all these things. We need VA, which is not difficult, right? Well, we have to find VA first, then we can find L because VA and VA prime are connected by L. Then we need W by L, for which we use this rather complicated, well, it's not complicated in the sense that it's just the current formula, but because of the early voltage presence, we have to factor in this also. But from here we can find W by L if you know everything else. The more important thing is to find VG3 and VG4, which are the bias voltages at the at the gate of both of these devices. Okay. Now the formula for ROP, I've repeated it here. So this is used as the first step in the solution. Then he first finds VA. Yeah, you can see how he uses the 500K formula, because each of these GM, RO, they all have VA that they use. So, and this is given 500K, so you can find VA. So that's what he does, and that's 2.74 volts. From there he can find L because VA prime is given, so L is 0.55. Then comes a little bit of the interesting part, which I think is important to understand. Firstly, he finds VSG4 0.5. Yeah, VSG4, he uses this formula. He doesn't mention the formula, so it may be a little confusing, but I've got this here. So VSG4 is VTP, which is 0.5, the absolute value, plus the overdrive voltage, which is given. So VSG4 is 0.8. Now, another formula for VSG4 that connects the gate bias to the SG drop between source and gate and VDD. So this formula uses then to find VG4 as 1 volt. Okay, so make sure you see how those steps in the middle, he uses these formulas to get them. One other thing that is interesting is that to find the largest possible swing at the output terminal, so assuming this is the output terminal, which it doesn't show but I added this, at this terminal if you want the largest possible voltage, then the least possible drop should happen here and here, right? So that almost all of VDD minus this comes out. So what is the minimum possible drop on Q4 and Q3 across the source and drain, That is VOV. Okay, so he makes the point that if VOV is the only drop here, then you get the maximum possible. So first you can find the voltage here at VD4 as VDD minus VOV, one drop. Then you can find the voltage here as this VD4 minus the VOV. Okay, so two successive VOVs give you the maximum output voltage here, which is also VD3 max as he calls it at the bottom of the page. That's 1.2. So 1.8 minus 0.3, that's 1.5, minus 0.3, that's 1.2. So you see how he gets that. Okay. Then he also uses the same formula to find VG3. Okay. Instead of VDD, now you put whatever was at VD4, which is 1.5, right, in this formula. Then at the very last step, he finds W by L using this, because everything else is known, right? So, interesting problem, a lot of good ideas. I see many of these same themes, same formulas repeated in the remaining 4 or 5 problems that I have solved from the back of the chapter. But again, this is important. And this note here, to allow for the largest possible swing at the output terminal, we shall use the minimum required voltage across Q4, which namely, when they say a voltage across a transistor, it means the, in this case, the source to drain voltage. So that if you allow that to be just VOV, then you get the maximum possible. Okay? Because any voltage across, higher than that is just driving it deeper into saturation, right? But if you just have VOV, that's good enough. It's already in saturation. All right, so after that, I will now look at some of my problems. Which I have to use my PDF. So let's see. So we are on page 25. Oh, next page 26, we have a problem, and this is problem 725. So, sorry. I have to find my document. Okay, here it is. Give me 1 second. All right. So 725 has this cascode with 4, it's a full cascode, right, with 4 transistors. The basic gain cell, its cascode, and these are both NPNs. The source load transistor and its cascode, both of them are PNPs. So all devices have a VA of 4 volts, and they have also supposed to operate at a given overdrive voltage of 0.2. So with this, find the transconductance GM1, the output resistance of the amplifier RON, which is this RON, amplifier meaning this portion, the output resistance of the current source, which means this ROP, the overall resistance RO, which is the parallel combination of RN and RON and ROP, and then the voltage gain. Okay, so all transistors are operating at the same current, which flows all the way from top to bottom. The formulas for GM and RO are given. Same formula pretty much applies to all. Then we have these formulas for RON, ROP, RO, and the gain is then just GM1 times RO with a negative sign. So straightforward applications of these formulas. So that's what I'm done here. Sorry, this one, yeah. So GM1 first is 2ID by VOV, which is 2I. I'm just replaced ID by I. So GM1 comes out to be this value, 2 milliamps per volt. Now all 4 devices have the same GM1 or GM basically, because they all have the same I, and all 4 devices also have the same RO, because RO, they have the same VAs, I is the same, they all have 20 kilo ohms as the RO. RON, this formula 800K, ROP, also the same formula, you get another 800. So RO equals 400K. It's the parallel combination. Hence gain is minus 800. Okay, so pretty straightforward application of formulas, but make sure you do this for practice yourself so that you get familiar with the formulas and the various parameters like G, M, RO, RON, ROP, and all that. All right, I'm going to move to the next problem, and this is problem 730. Okay, here also we have the 4 transistor full cascade, both the gain cell and the source current, source load current device, both cascaded. Now here VI is given to be 0.6 volts. The DC component at the input, meaning the bias voltage VI is V 0.6. So why you couldn't have just said V? I guess because this is where the input signal is, right? So the voltage here is the sum of VI, the signal, plus VI, capital VI, the bias. So he's just given the capital VI, which is with V input, which is 0.6. Also he's given all these other values, which is neat. VG2, VG3, VG2, VG3, VG4 is given, VGD is given. All devices are matched, so these are the same and have equal VT of 0.4. So they all also have VT, both VTN and VTP is given to be 0.4 for the PMOS and the NMOS. What is the overdrive voltage? So here we have to find VOV. What is the allowable voltage range at the output? So these are 2 important questions to answer. So the formulas to use, VGS, which is this portion here, I put that VGS symbol and the VSG symbol here because they're not in the figure, but I added them to make it easier to understand. So VGS, which is V input, the DC portion, is another formula is VT plus VOV, right? You should know this by now. So from here we can find VOV. Another formula that you can use here to find VOV, actually they should all be the same anyway, but here's another one to check. So VSG here, this is PMOS, so the reverse formula, VSG is VDD minus VG4, right? That's another formula. So there we can find, so that's one. Also VOV, this formula applied to PMOS, and keep VOV here and move everything to the other side, you get as VSG minus VT. So this way also, if you do VOV, you should get VOV, and it should be the same because they are all matched devices. Okay. Then we answer the question about the allowable voltage range. Okay. All right. So let me go to problem 730. Since the four devices have equal Ks and the same bias current I, their VOVs will be the same. At Q1 VGS, using this formula, we get VOV equals VGS 0.6 minus 0.2, sorry, VT is 0.4, right? So this should be minus 0.4. Yeah, sorry, VT is 0.4. So this should be and then you get 0.2 as the VOV. Continuing at Q4, you can do the same things to check. First you find VSG, then you can find VOV as 0.2 also. So this 0.2 and this 0.2, they match. Now at the output, right, V0, or sorry, VO is the output. So this is where the output is. It's coming out of this Q2 transistor, right, here, and ground. So maximum voltage VO max happens when each transistor sees a minimum allowable voltage across it, that is the VDS should be equal to VOV, which is 0.2, right? This is exactly the condition that I just talked about in the previous example, right? So using that drop across each transistor and starting from the top, here we have 1.3, then here the drop is VOV or 0.2, the drop is VOV of 0.2, then what we get here is 1.3 minus 0.2 minus 0.2, which is what I do here to get 0.9. Okay. Then minimum allowable voltage. Now this is the point at which Q2 goes from saturation to triode, right? And this I had to bring in a slide from our previous chapters to kind of illustrate what we are talking about. So A was the maximum, which is generally VDD, but because we are not at VDD but we are going down, right, each of these transistors, VDD is here, and once you come here it's VDD minus something, then you come here, that's VDD minus something, right? So that's why we couldn't use VDD directly, but we used VDD minus VOV minus VOV. This point B, this is the formula, pretty straightforward. The VDS here is VGS minus VT. Okay, so the drain to source voltage here is VGS minus VT, and so using that directly, we know the VGS is gate to source is given, gate 2, as 0.9, VT is given as 0.5, so you get the minimum as 0.5. So the allowable range at the output is 0.5 to 0.9 volts. Okay, I hope this is clear, because we were given this, right? VG2 was given to be 0.9. Okay, so moving on. I don't know what this is. Next problem is 733. So here the amplifier and its cascode are shown. And this problem is actually related to the voltage gain business, right? You remember how we said if you have such a cascode, then you can tell what is the gain from Q1, what is the gain from Q2 separately, right? The gain from Q1 is A1, the gain from Q2 is A2, and so on. So that's the subject of this problem. But before that, he also has something else here. So let's read the problem. A CMOS cascade amplifier, such as shown here. Actually, this is, let me just take that out to avoid confusion, because some of these problems are from the 7th edition of the textbook. So that's why it refers to, chapter 8 figures. But continuing here, so identical common source circuit and common gate transistor. Common source transistor for the gain cell, common gate transistor for the cascode, okay? The current mirror, as we call it. So, if I have not mentioned it ever before, I hope I did, but the cascodes are always common base or common gate, right? I think I've mentioned that. Okay. So a CMOS cascode amplifier has identical transistors with the same W by L, and they're biased at one current point too. The fabrication process also gives these values for K and VA prime, the early voltage. At what value of RL does the gain AV become minus 100? So if you're given now, you want to find not the open circuit voltage, but the actual voltage with the load resistor connected, and that gain has to be minus 100, right? And second part is of course related to the gain of the common source stage, that means the Q1. All right. So given this on slide 32, how do we go about solving the problem? So overall voltage gain, including the load resistor, is this formula. This is an old formula. I'm sure you're comfortable by now. How do we find GM1? This is a formula. How do we find RO? Here's a formula. RL is of course given to be, well, we have to find RL. So if the gain has to be minus 100, so you substitute for minus 100, then you can find RL. Okay. Then to find A1 separately, we have to find something called RD1. To find RD1, we have to find something called RN2. And RN2 has a formula which I didn't write here, but it's in my notes, so you can see how that's done. All right. So let me reduce this 733, and here we go. So starting with GM1, which is also GM2, use this formula. Everything is given here, so you come up with 1.55. Next, we have RO1 formulas, which is simple. VA prime L by ID. So this comes out to be 9K. With those two values, we can find an RO1, RO2, they're all the same, right? RO becomes this, 143K. AV is now this. And from there, from this formula, you can find RL, which was the remaining resistor, at 117 kilo ohms. To find A1 is minus GM RD1. RD1 is RO1 in parallel with RN2. RN2 has this formula, we have seen this before. you see this factor in the denominator, right, about which we read a little more. So using this formula, you get this to be 10.2. Then RD1 becomes 4.8 as shown here. Finally, gain is minus 7.41. Okay. So I think it was a simple problem, but you see how the application of, I think we studied this here. See all these formulas in this, how to find the voltage gain of each stage separately. Now he didn't ask us for the gain of stage 2 separately, but if you know the overall gain and the gain of one of the stages, now the overall gain was 100, that's given, right? And the gain of first stage is 7.41. You can see that a lot of the gain is happening in the second stage, right? Were we given the gain? Hold on, let me not get confused. Yeah, 100 is given, right? Okay, so 100 is the overall gain. Gain of one stage is 7. So the other stage, this stage has about 14 or 15 gain. Yeah, so or 13, I think. So that solves the problem too if it was asked. Okay, I'm gonna move on. We've got a few more to do. This one is about double cascoding. Okay, so we are only cascoding the source, the current load source. Current source load. I keep mixing that up. Current source load. So this is what is being cascaded using two other transistors. We are not looking at the bottom portion where the gain cell, the amplifier itself, is present and its cascode. We are only focusing on the upper section. And all these are PMOS because generally this is a PMOS connected to a positive VDD. Okay. So design the double cascode current source shown to provide 0.2 milliamps and the largest possible signal swing at the output. So how do you get the largest possible? He tells us himself, design for the minimum allowable voltage across each transistor. So the minimum across each V source to drain should be minimum, meaning it should be VOV, V overdrive, right? So that is one condition. Then some other parameters are given about VT, VA prime, K, length is also given, and VOV is given. So many things are given. We do have to find VG1, VG2, VG3 and the W by L ratios. Finally, what is the value of the output resistance achieved, which is just as seen up into the source, current source. Okay. All right. So minimum allowable value VSD, I'm just showing you, is VOV. Important to recognize that. Then RO has this. GM and RO has these formulas. Yeah, we need a GM and RO here in this formula. So I'm showing you how to get GM and RO. By now you should know this. And then W by L, you get it like this. Now, how to find the VG1, VG2? Sorry, I haven't shown the formulas, but it's in my notes. So let's go through it. 737, right? So let me get past this and we look at 737. So how many more problems do we have? 712. Oh, that's it. Only one more after this. Okay, so PMOS devices. So the minimum allowable voltage V source to drain across each of Q1 and Q2 is 0.2 VOV. So the voltage at drain of Q1, so what that means is, you start here, this is the source of Q1, drain of Q1, right? At this point, what is the voltage? 1.8 minus VOV, which is 0.2, so you get 1.6. Similarly, voltage at the drain of Q2, which is here, right? So whatever was here, 1.6, might take out another 0.2, so you get 1.4, and so on. So for Q2 drain, it's 1.4. For Q3 drain, it's 1.2. So once we have that, then we can see other formulas that we can use. For example, to find the voltage at the gate, you can do this, right? VDD minus, actually the formula is generally given with this on this side. That means the V source to, well, that's fine, yeah. VG1 is VDD minus VSG1. In this case, VDD, because this is directly connected to VDD. If you are looking at this transistor, then instead of VDD, we put whatever is the voltage here, which is at the source of Q2, which is also at the drain of Q1, which we just calculated as 1.6. So that same formula can be used. Instead of VDD, put whatever is the voltage there. Okay. So VG1 is VDD minus VSG1. What is VSG1? You need another formula for that because we don't have that source to gate, right? Which would be this to this. We don't have that directly, but there is a formula for it in terms of VTP and VOV. This is your basic formula, right? This formula tells you that a transistor is operating in saturation, right? What is the output voltage? Has to be above VOV to be in saturation. So anyway, the formula for VSG by definition, or rather, what is overdrive voltage? It is VSG minus VTP, right? That's how we define it. What is the overdrive voltage? It is the source to gate voltage minus the VT. So we are just redoing that, but this is an important formula for VSG1, which is VTP plus VOV. So using that, you come up with 1.8 at the gate of VG1. So this voltage is 1.2. 1.2. Similarly, VG2, we don't have VDD like I said, but we have VS2 at the source minus SG2, which is again 1.6 minus, for SG2 use VTP plus VOV, and it's the same everywhere, 0.4 plus 0.2. So 1.6 minus 0.6, so you get 1. So 1 is the value here at the gate 2. Now remember, these are the values we need to find anyway. I'm not wasting your time. I'm doing what they want us to do. Similarly, VG3 is VS3 at the source of transistor 3 minus the VSG3. This is VS3 minus VSG3. So VS3 is 1.4. We found that using this method, right? This method. This is at the drain, which is also the source of the next transistor. So it's 1.4 minus VSG3, which is the same business again. Add the overdrive and the VTP, and you get 0.8. So thus we got 1.2, 1 and 0.8 for the 3 gate voltages, right? This voltage, this voltage, this voltage. Okay. Now we need to find W by L. That's pretty simple. ID equals this. So you can get W by L by reversing it. and that value is 100. Okay. Lastly, we need to find RO, which we know has its own formula, GMRO square into RO, and GM is this, RO is this, so we can just do this. So GM is 2 milliamps, RO is 12 kilo ohms. So if you multiply the two, first square it, then one more time multiply by the RO, you get 6.91 mega ohms for the output resistance as seen into the upper portion, right? This is, I think they call it ROP in some figures that we have seen before. Okay. All right. After this, I only have one example. There's many other examples. Actually, this is an exercise. This is not an example or a problem, but the answers are given below, and we just need to work them through and get the answers. Then I also have some problems for you in the homework. There's a lot of problems in this section, but I think if you look at these problems, the examples in the textbook, and what I'm going to give you for homework, you should be, reasonably well prepared to take my at least be well prepared for the quizzes and all that. All right, so what is 7.12 asking us? Consider the BJT cascode amplifier of figure 7.19. So where is 7.19? This is 7.19. Now we have finally come to BJT cascodes, right? And this is a full cascode, meaning 2 NPNs, 2 PNPs. Current source load has its own cascode, and the gain cell, the common emitter, has its own cascode consisting of a common base amplifier, because this is a common base amplifier, while this is a common emitter amplifier. Okay. All right. So this circuit is what we are talking about. It has a current of 0.2 milliamps, constant all the way top to bottom. Assume that NPN transistors have beta equals 100 and VA equals 5, and that the PNP transistors have lower beta and VA is slightly different. So for the NPN transistors we got some numbers, and for the PNP we have some numbers. So find RON, ROP and AV. Also use the result of exercise 711. Now 711 I have not touched yet, but 711 is actually deriving a formula, and that formula I've repeated here. So the formula is for the maximum achievable gain. So we'll find some gain, but that isn't necessarily the maximum achievable. So you can see the difference here in the answers. The gain we'll find is minus 4186, but the maximum is minus 5714. So how do you get this? There's another formula. Okay, so pretty straightforward. I don't think this is too difficult. For NPN or BJTs, you need to find these three parameters: transconductance, input resistance, output resistance for the devices. Then the output resistance for the whole network or the whole circuit. This is RO. Well, there's a positive and a negative. Sorry, not positive, negative. For the NPN device, it's RON. For the PNP device, it's ROP. Similar to what we had for the CMOS, where for the P devices, which were the current load source, those had ROP, and for the gain cell, which were NMOS devices, we had RON. So same thing here also, you have formula for RON, ROP, but they basically, well, in this case they won't be the same. Maybe. We'll see. Yeah, they won't be the same because beta is different, right? So our pi will be different. Yeah, we are getting 1.67 and 0.762. So they are definitely different. All right. So with these formulas and this other formula, we should be able to finish, and I may be able to finish on time for a first time ever, right? All right. So this is a BJT cascode. NPN portion, PNP portion. GM1 equals GM2 is IC by VT. You do that, you get 8. R pi 1 input resistance is beta by GM, you get 12.5K. The two output resistances, 25K for each transistor. Hence, RON is this formula, the parallel in it. So if you do that, you get 1.67 mega ohms. I think that's what's given, right? Yeah, 1.67, 0.762. GM3 equals GM4 for the PNP side, which is also, same formulas, 8, 6.25, 20. So ROP comes out to be this, 762 kilo ohms. AV, you do with this formula, you get minus 4186. AV max occurs when RO1 and RO4 are much greater than R pi. So the amplifying resistance, output resistance of the amplifying transistor and the output resistance of the current source load transistor, if they are each much higher than this, then you can use this formula to find AV max. That was in the previous exercise that we skipped, but using this formula you can get AV max. Okay. All right, so that covers most of the important topics of this section of chapter 7, which is the cascode business. Again, please do the homework and all that. You can polish your knowledge of this, practice what I've done here, look at the examples, and you should be good for tests and so on. All right, next recordings we will look at section 7.4, which talks about current mirrors and so on. So I will begin that in my next recording pretty soon. All right, take care.